Our next video here discusses related rates, and there's really nothing new as far as the calculus in this section other than we're going to be looking at word problems that put to work our skills with implicit differentiation. So whenever we're doing problems like this, you're going to need to keep a few things in mind. Now, a lot of these are just common sense, but you do need to make sure you read the problems carefully, draw a diagram whenever possible, and especially on the more difficult problems, that'll certainly be possible and important to do. Introduce notation, so you're going to need to know that if I say something like the horizontal displacement is changing at a rate of 5 feet per second, well, we're going to need to call that dx dt, the change in the horizontal over the change in time. So important quantities like that are going to be coming up, and notice I said that in the next step as well. Express any given information in the relate in terms of derivatives. So not only will you be labeling sides like x, y, and z, but you'll be labeling the rates of change like dx dt, dy dt, and dz dt, how fast each is changing with respect to time. Now, the final step here, our goal is to write an equation that's going to relate every variable in the problem. And then, if necessary, we're going to use geometry. The geometry techniques that come in handy in this section will be similar triangles. We'll use that on several of the problems. Other things that you'll need to remember from trigonometry, your SOHCAHTOA, right trig triangle terminology. We'll use law of cosines on some of the more beautiful problems. So a bunch of different things will come up into play. Let's go ahead and look at some of the problems here. Now, the first one, and these are done in kind of order of difficulty, so this first one should be very straightforward. I'm saying that if A is the area of a circle, and we know area of a circle is pi r squared, with a radius r, and the circle expands as time passes, I'm asking you to find, this is read as the change in area with respect to time, so the derivative of area with respect to time in terms of the change of the radius with respect to time. So that should make sense to you. If we have a circle here of radius r, if we're going to say that that radius is growing, well, clearly the corresponding area is going to grow. Well, our formula here, I said area is equal to pi r squared. So in this problem, if area is pi r squared, then I need to take the derivative of that equation with respect to t. Well, the derivative of area with respect to time is simply just dA dt. On the right hand side, you need to think of that r as being inside of a group. The 2 would come down in front, times r to the first times the derivative of the inside, which is going to be dr dt. So the derivative of my right hand side is going to be 2 pi r dr dt. Now, that's all I ask for in part A. I asked for an equation stating the change in the the change in the area with respect to time in terms of the change in the radius with respect to time. So we have that. But now, in part B in this problem, I said, suppose oil spills from a ruptured tanker and it spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters? Okay, so here in this problem, all I'm giving you is information to plug in to solve out for how fast the area of the oil spill is increasing at a specific time t. So what I was given in part B here is that the change in the radius of the oil spill was increasing by 1 meter per second when the radius of the spill was 30 meters. So notice I just plugged that into my equation down here. I can say the area is increasing at a rate of, with respect to time, 2 pi times r. Well, r was 30 meters, dr dt was increasing at a rate of 1 meter per second. I multiply that out, and I can see that the area of the oil spill is increasing at a rate of 60 pi square meters per second. Now notice that square meters, that's the change in the area. Every second that that area of the oil spill is going to increase by 60 pi square meters, and that's per second, per change in time. Change in area over the change in time. So this gives us our instantaneous rate of change of our area at the specific instant in time when the radius of the oil spill is 30 meters. Now, it's not going to be relevant for other points in time, but when the radius is 30 meters, we know that that is the instantaneous rate of change of the area at that instant. Now, for my next problem here, if I give you, here in this one I say a particle moves along a curve and it's just the square root function, the square root of 1 plus x cubed. As it reaches the ordered pair 2, 3, you're told that the y-coordinate is increasing at a rate of 4 centimeters per second. So instantly there, guys, you need to pick up, okay, y-coordinate is increasing at a rate of 4 centimeters per second. That's the change in y over the change in time. That is dy dt. How fast is the x-coordinate at that point changing at that instant? So our goal of the problem is dx dt. Here's how I worked it. This was the equation given in number 2. Now, we were given that the y-coordinate was changing at a rate of 4 centimeters per second. So I have that labeled as dy dt. And you know that y is changing at that rate at the point 2, 3. So we know x is 2 and y is 3. So now my equation, I went ahead and wrote with the 1/2 exponent instead of the square root. That makes it easier to take the derivative in the next step. Well, the derivative of the left-hand side with respect to time is simply dy dt. The derivative of the right, the 1/2 comes down in front of the group, times the group to the negative 1/2 power, times the derivative of the inside. Now be careful here. Derivative of x cubed, yes, it is 3x squared, but then you say times the derivative of x, chain rule here, and you say, well, if it were the derivative of x with respect to x, you wouldn't need anything on the outside here. dx dx is just 1. But we're taking the derivative with respect to t, so the derivative of x has to be dx dt. So you need to remember, in this section specifically, anytime you're taking the derivative of anything containing a y, you better put a dy dt because we're taking the derivative with respect to time. Anytime you take the derivative of an x, you're going to have to put a dx dt after it. So now, when I go down to the next step, you'll notice once you take the derivative, you can start plugging in information. I could not plug in that I knew x was 2 and that I knew that the y value was 3. I could not plug that in here because these are variables. Anything that varies must stay a variable until the derivative is taken. And now once the derivative is taken, I can start plugging things in. So I'm trying to solve for dy dt. So I know that the dy dt in the, I'm trying to solve for dx dt. I know dy dt is 4 centimeters per second. So you'll see I plugged that in. I know x from the problem is 2. So 3x squared becomes 3 times 2 squared over 2 on the square root of 1 plus 2 cubed. All of that times dx dt, which is what we're solving for. This simplified to just be 12 over 6. 12 over 6 is 2. So I know 2 dx dt is 4. I just divided by 2 on each side and got dx dt was equal to 2. Now I know that the answer is also in centimeters per second. It's the exact same measurement as the dy dt. X and y are measured in the same units in this problem. So we'd say the x coordinate is changing by 2 centimeters per second as it nears the point 2, 3. Now, a much more fun problem. 1 and 2, not that fun. 3, gorgeous. We're told at noon, ship A is 150 kilometers west of ship B. Then you're told that ship A is sailing east at 35 kilometers per hour and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Glorious problem. Here's how I solved it, guys. So first of all, unlike the previous 2 problems, I really didn't need a diagram for those. I drew a circle in 1, but I didn't do anything with it, and I didn't have to draw anything in 2. It would be hard to do this one without a drawing. So when I'm thinking about this, I can say, okay, originally, and notice I put A sub 0 and B sub 0 for the original position of ship A and the original position of ship B. That is not the position at the point of interest. So I label those A sub 0. So I know that A is originally 150 kilometers west of B. That's why I have this distance down here labeled 150 kilometers. But now you know that A is traveling east at a rate of 35 kilometers per hour. Meanwhile, B is traveling north at a rate of 25 kilometers per hour. Well, they start this at 12 p.m. and we're interested in how fast they're moving apart at 4 p.m. So over here, I came over here and said, well, I need to find out how far east is A traveling. Well, it's going 35 kilometers per hour for a total of 4 hours. So 35 times 4, 140 kilometers. Now, you'll see that I have that distance labeled here. So I know A is still short of the original position of B. It was 150 kilometers away from the original position. Now it's going to be 10 kilometers away from the original position of B. Now B, meanwhile, it's no longer at its original position because it's been traveling north at a rate of 25 kilometers per hour for 4 hours. So it's went 100 kilometers north. I went ahead and labeled this triangle here because I need to know how fast the distance between them is changing at 4 p.m. Well, the distance between them would be a triangle hypotenuse where the base is 10 kilometers, the horizontal distance there, and the vertical distance being 100 kilometers, the distance that ship B has traveled north. So I can easily say, well, Pythagorean Theorem, x squared plus y squared is equal to z squared. I know x squared and y squared here. So I went ahead and solved for what z is equal to. I said that's going to be 100 plus 10,000. Z squared is 10,100. Well, I would rather keep that exact and say z is just the square root of 10,100. Now, here's the thing. Whenever I'm trying to find out, and the goal of this problem is not to find out how far apart they are, but how fast that distance is changing. So the goal of the problem is to find dz dt. Well, I need to find an equation involving all variables. Well, Pythagorean Theorem gives me that equation. But now I need to use the Pythagorean Theorem, x squared plus y squared is equal to z squared. I cannot nor should not go ahead and plug in what I know x and y is. Before you can take a derivative, anything that varies must have a variable. So please make sure you see in this problem, is x always going to be 10? No, it's only 10 right at 4 p.m. Same thing with y. Is it always going to be 100? No, it's only 100 kilometers at the instant of 4 p.m. And again, z, is the distance between them always going to be this? Again, no. That distance is going to change. Anything that varies must stay a variable before we take the derivative. So I said, well, everything stays a variable. Now take the derivative. This gives me 2x dx dt plus 2y dy dt. Derivative of the other side, of course, 2z dz dt. So that's, and again remember, that's not taking the derivative with respect to x like we're normally used to. It's the derivative with respect to t. So that's why they all have the dx dt, dy dt, and the dz dt beside them, because they're all functions with respect to time. Now that I've taken the derivative, I start plugging things in. And you'll notice from this step to this step, I also just divided each side by a factor of 2. There was no point plugging those 2's in there. Just divided both sides by 2 to make it easier. And then I plugged in the x. Well, the x that I know in the problem is 10 kilometers. Had to plug that in. Now, dx dt, here's where I think a lot of people are going to go wrong. They'll look up here and they'll say, well, but wait a minute. Ship A was traveling east at a rate of 35 kilometers per hour. Why are you putting negative 35 in your problem? And the answer to that is because I must with how I have it labeled. Please make sure you look up here and say, okay, dx dt, What is that supposed to represent? It's supposed to represent the change of the variable x. Look at how x is labeled. X is labeled as the distance between ship A and the original position of ship B. At 4 p.m., is that distance going to be increasing or decreasing? So 1 minute later, is it going to be more than 10 kilometers distance or less? And you know the answer to that is, oh, it's going to be less. Well, then dx dt must be negative since x is decreasing at the point of interest. It's decreasing by a rate of negative 35 kilometers per hour at that instant. That's the most common mistake I see students make in these problems, is not putting the correct sign for the derivative when they plug it in. Now, my y variable, clearly that's 100, and I don't have to worry about the sign of dy dt. It is increasing the distance of that 100 at 4 p.m., so it's a positive 25. On my other side, I put my z, the square root of 10,100, times dz dt, which is, I know, the goal of the problem. So now I can say, well, dz dt, this is just going to be negative 350 plus 2,500. I'll divide by that square root of 10,100 on both sides. My numerator would simplify to be 2150 over that root. I can say that's my exact answer for dz dt. I plugged that into a calculator and I got 21.393 approximate. And then you'll always need to put units by your final answer. This is in kilometers per hour. And now that should make sense to you. The distance is being decreased by A because it's getting closer horizontally, but B is lengthening the distance vertically. So it's not quite going apart at a rate of 25 kilometers per hour, but almost that full rate. They're going apart at a rate of 21.393 kilometers per hour. Now, keep in mind, if I would have said how fast is their distance changing at 5 p.m., it would be dramatically higher than that, because then your ending position for A would be on the other side of the original position for B, and then your horizontal displacement and your vertical displacement is increasing, and you would see a dramatically higher change between the distance of the two. Okay, excellent problem there. Moving on. If we look at a different type of problem, number 4, this one is, in fact, the next two, they're going to be the ones dealing with similar triangles. It says you have a street light that's mounted to the top of a 15-foot pole. You have a man that's 6 foot tall that's walking away from the pole with a speed of 5 feet per second. And he's walking along a straight path. How fast is the tip of his shadow moving when he is 40 foot from the pole? Okay, so let me show you how I would explain how to work that problem. So I'll keep my number 4 problem right here and my information to solve it right below it. So I know I have the 15-foot pole. That's the first thing I would have drawn, just because, and I know that this is probably going to be a triangle, 15 foot. And then I have a man that's walking away from that pole at a distance of 40 feet. I'm not going to put my horizontal and vertical to scale. That would make my horizontal way too long. So I just said, let's let that equal 40 foot. And the man is 6 foot tall. And we know the man is walking away from the pole, but we're trying to find out how fast the tip of his shadow is moving from him. So clearly, as he moves away from the pole, the light that pole shines over his head is going to generate a shadow on the ground. The goal of the problem is to find out how fast that shadow is increasing. So my goal is dy dt. Now, I know he's walking away from the pole at a rate of 5 feet per second. So you'll see here I have labeled his distance from the pole is 40 feet. I must also label that x because that distance is not a constant. Anything that varies must have a variable. So I labeled his horizontal distance from the pole x. I don't have to label the height of the pole anything because that's not changing in the problem. You'll see that's just 15. Nor do I need to label his height anything. It's not changing. It's going to be a constant of 6 feet. But I do need to label the distance the tip of his shadow is from him something. Typically, I like to label any horizontal change x, but that's already representing his distance from the pole. So I'll let y represent the distance the tip of his shadow is from him. Now we don't know what y is in the problem, we may not need to. Our goal is not to find y, but to find dy dt. So the first thing I did was I went ahead and I created a large triangle ABC, and then I wanted you to see that we could generate a small triangle within that large triangle, DEC, that's similar to ABC. And to make sure you understand what I mean by similar triangles are triangles that have all equal angles. Notice angle A and angle D have to both be right angles. Angle C is the same in both triangles, which means angle E has to be the same as angle B. Now, if all the angles are the same, that means that sides are proportional. So that means the height over the base of the large triangle should equal the height over the base of the small triangle. So I said 15 over x plus y should equal 6 over y. And this allows me to get an equation involving all variables in the problem. So it's a pretty simple equation too. All I did is I cross multiplied 15y equals 6 times x plus y. Then I said, well, okay, let's go ahead and subtract 6y on both sides. That gave me 9y is equal to 6x. Then I divided by 9. 6 over 9 is 2/3. I just get y is equal to 2/3 x. Now that I get to that point, I take the derivative of both sides. Derivative of y is dy dt. Derivative of x is dx dt. So I know that the change of y with respect to time is 2/3 the change of x with respect to time. This makes it very easy to find out how fast the tip of the shadow is moving, because it's just 2/3 of how fast he's moving away from the pole. So I just say, well, his distance from the pole is, or sorry, the rate he's moving away from the pole is 5 feet per second. I plug that into my problem, and I know that the tip of his shadow is moving away at a rate of 10/3 feet per second. So now, another problem, extremely similar. This one's a little harder, but still pretty good. So let's say you have a spotlight that's on the ground. It's shining on a wall 12 meters away. You've got a man that's 2 meters tall that's walking from the spotlight towards the building at a speed of 1.6 meters per second. Our goal is to find out how fast the length of his shadow on the building is decreasing when he is 4 meters from the building. Okay, so whenever I'm trying to think of that problem, I can say, well, all right, let's draw out the scenario. So we had a spotlight on the ground that's shining on a wall 12 meters away. So the distance from the spotlight to the wall is 12 meters. Now we had a man that said that he was 4 meters from the wall, so I went ahead and labeled that 4, which means that his distance from the spotlight has to be 8 meters. Now I went ahead and also labeled his distance from the spotlight as x, and then his distance from the wall would be 12 minus x. At first glance, you may think, well, why do you even need variables there when you know that this is 4 and that is 8? It's because it's changing. Anything that varies must have a variable. So only at the instant that I'm interested in is his distance from the wall 4 meters. He's moving towards the wall at a rate of 1.6 meters per second. So that's why I wanted to go ahead and label these as variables too. And then I went ahead and labeled this as x as opposed to this x, because if I allow his distance from the spotlight to be x, then the change of x with respect to time can be positive. So let's say, for example, I would have called his distance from the wall x. Then dx dt would have had to be negative 1.6 meters per second, since that distance would be decreasing. But since I'm letting x represent his distance from the spotlight, positive 1.6 meters per second is fine. Now, I thought of the big triangle here as ABC, and then I drew a small triangle in here, ADE. They both have the angle A. Angle D and B are both right angles, thus E is equal to angle C. Since all angles are the same, again, we can set up proportions and say the height over the base, and the entire base of the large triangle is 12. The height over the base should equal the height over the base of the small triangle, and do not call that base 8 because I need an equation that I'm going to take the variables. So anything that varies must have a variable. The overall base of the large triangle isn't varying. The distance the spotlight is from the wall is always 12. The only thing that's varying in the problem is his distance from the wall. So that's why I said y over 12, and then 2 over, not 8, but 2 over x here. Now I go in and I try to work this out. So I cross multiply it again, and I got x times y is equal to 24. So then I can say, well, let's divide by x on both sides. Instead of saying the right-hand side is 24 over x and having to use the quotient rule, I preferred to call it 24x to the negative 1. At that point, go ahead and take the derivative. Derivative of the left is dy dt. Derivative of the right, the negative 1 comes down in front, making that negative 24 x to the negative 2 times the derivative of x, which is your dx dt here. So now I just need to simplify this out, and I can say, well, okay, I'll get negative 24 over x squared dx dt. In this problem, that's going to be negative 24. Notice x is 8, so that's where the 8 squared comes from there, times dx dt. We know dx dt was 1.6. I multiplied all of that out, and I got a negative 0.6 meters per second here. Now please keep in mind, you cannot start plugging things in for x or dx dt until you've taken the derivative when you're trying to solve for a rate of change. Okay, next problem. For number 6, you're told that a boat is pulled into a dock by a rope attached to the bow of the boat, and it's passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, not a bad problem at all. Here's my solution for it. So you have the boat. It's 8 meters away from a dock, and that dock is located 1 meter above the bow of the boat. So now, anything that varies in this problem, you need to put a variable. Notice I didn't put anything for the vertical here. That 1 meter is just how high above the dock is above the boat. That's not going to change in this problem. So the location of that dock above the water isn't going to change, so that stays a constant of 1. There is no need to call that y. However, the distance the boat is from the dock, it's certainly changing. It's being pulled in towards the dock. Only at the point of interest is it 8 meters away, so I also need to call that a variable x. Now, the length of the line that you need to pull the boat in is also changing in the problem, and in fact, we're told that the boat is being pulled in, that the rope is being pulled in at a rate of 1 meter per second. So I'm going to let z represent the amount of rope distance from the dock down to the boat. And please notice why I'm calling dz dt negative. That's extremely important here, guys. Z is not going to increase. The boat's not going to go further out. The boat is coming in, which means that hypotenuse is decreasing as that rope is being pulled in. Has to be negative 1 meter per second for the dz dt. Now, I went ahead and solved for z as well, and I said it's just the hypotenuse of a right triangle, so z squared is equal to 1 squared plus 8 squared, which gives me z squared is 65, z is the root of 65. I'll keep that exact. So now I use that exact same Pythagorean theorem, but I say instead of plugging in terms for anything that I know, I have to keep any variable as a variable. So you'll notice I didn't say 8 squared plus 1 squared. I said x squared plus 1 squared is equal to z squared. Anything that varies must have a variable before you intend to take the derivative. Now I have my variables in there. I can take the derivative. Derivative of x squared is 2x dx dt. Derivative of any constant is 0. Derivative of the right-hand side, 2z dz dt. At that point, I went ahead and just divided both sides by 2 and got x dx dt equals z dz dt. Now that you've taken the derivative successfully, you plug in what you know to be true. In this problem, we know x is 8, so I plug that in for x. We don't know dx dt. That's the goal of the problem. How fast is the boat being pulled in towards the dock? So I can say, well, okay, dx dt, I don't know. Z in this problem. Z was my distance of the rope. It's the square root of 65. dz dt was the rate at which that distance was changing. It's being pulled in at a rate of 1 meter per second. So now dx dt is just going to equal the negative square root of 65 over 8, and I got a negative 1.008 meters per second. So we can say that the way we would interpret that answer is the boat's distance from the dock is decreasing by 1.008 meters per second when it is 8 meters away from the dock. So the distance is decreasing, which is why the derivative was negative in that case. Up next, a lot of people think that this next problem, well, actually the next four, usually people struggle with all of them, but a lot of people really don't like this next one. Let me make sure I do as good of a job as I can making you comfortable with this problem. So we know that water is leaking out of an inverted conical tank, and it's leaking out at a rate of 10,000 cubic centimeters per minute. But at the same time, water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and a diameter of 4 meters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which the water is being pumped into the tank. Okay, here's my solution to that problem. So first of all, see, I drew an inverted conical tank. It said it had a diameter of 4, which meant its radius was 2, and it had an overall height of 6 meters. So I've just tried to label from the bottom to the top of the tank 6 meters here. Now, volume of an inverted conical tank formula in anything like this would be given in an assignment, but our volume formula is going to be 1/3 pi r squared h. Now, in this problem, we were told that the point of interest was when the height was 2 meters. I went ahead and converted that to 200 centimeters for the simple purpose that it said in the problem that the height was changing at a rate. So notice the water is being pumped in such that the water level is rising at a rate of 20 centimeters per minute when the water level is 2 meters. So the height of interest is 2 meters, which is 200 centimeters, and it's changing at a rate of 20 centimeters per minute. So this was given in the problem. Now, my goal is to find the rate at which water is being pumped into the tank. So the way I'm going to have to rationalize that is I'm going to call that the water being pumped into the tank dp dt, how fast water is being pumped into the tank at time t, dp dt. That's my goal. But now I can try to solve for dv dt, but remember dv dt, you have 1,000, or you have water leaking out by 10,000 cubic centimeters per minute. So I know that in order to account for that, dp dt is going to have to be whatever that the change in volume is plus 10,000 cubic centimeters per minute, because I know that dv dt is going to be how much water is being pumped in minus how much water is being leaked out. So if I try to solve for dp dt, it's just going to be the change in volume plus 10,000 cubic centimeters per minute. Okay, my goal, in order to get dp dt, I first have to find dv dt. So I go back to my tank picture, and I can say in this tank picture here, I can see some similar triangles. Notice you have a large triangle here that has a height of 6 and a base of 2. And you have a small triangle here that has a height of h and a base of r. So I just said by similar triangles, we know that the base over the height of the large triangle should equal the base over the height of the small triangle. So this is just showing you that your radius and that your height must be proportional at any height throughout the inverted conical tank. To see that in this case, I just cross multiplied and said, well, 2h must equal 6r. So h is 3r, or what I really needed was r in terms of h. So I said r is equal to 1/3 h. Now, the reason I went ahead and solved for r in terms of h is so that I could plug it in and get my volume formula solely in terms of h in my problem. The reason I want that, nowhere was I directly given what dr dt was. So I didn't want to take the derivative of an expression containing r because I would get a dr dt. I don't know what dr dt is explicitly, but I do know what dh dt is. So I substitute what I know r is equal to in terms of h into my problem right here. And then I can say, well, 1/3 h squared, that's going to give me 1/9 h squared. 1/9 times 1/3 gives me 1/27. I went ahead and wrote that as pi over 27, and then I'll have h cubed. So my volume formula actually simplifies really nicely to this, and then I can say, okay, now let's take the derivative. Well, the derivative of v is dv dt. Derivative of the right-hand side, you'll get pi over 9 when you bring the 3 down, h to the second, times the derivative of h, which is my dh dt. And then I can go in and say, okay, plug everything in that we know. We're trying to find dv dt. Well, dv dt is going to be pi times h squared. Remember, h was just your 200 centimeters. That's where I got that from. And then I can say times dh dt, that was the 20 centimeters per minute. I plugged that in. All of that's divided by 9. I went ahead and simplified this. 200 squared, that would be 40,000. 40,000 times 20 is 80,000. My numerator would be 80,000 pi, and then I have over 9 cubic centimeters per minute. But that's the change in the volume with respect to T. The rate at which water is being pumped in is going to be that change in volume plus how much was being leaked out. It has to make up for that amount. So plus 10,000 cubic centimeters there. I put this into my calculator and I got 289,252.68 cubic centimeters per minute. And again, please do note you need that units in your final answer for these questions. Now, that's the rate of the change of volume at the point in time where the height of the water is 2 meters or 200 centimeters. There's no guarantee that the change in volume is always going to be that rate. It's just at that instant in time. Next problem. The nice thing about the last three, you might be thinking, well, gosh, none of our problems thus far have had anything to do with trigonometry. That changes. So in number 8, you're told that you have a kite that's 100 feet above the ground and that it's moving horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the ground? And you're told that the kite is anchored to the ground. At what rate is the angle between that decreasing when 200 feet of string have been let out? Okay, let me show you how I approached this problem. So here's my kite anchored to the ground. 200 feet of string have been let out to where the kite is flowing, but yet the kite is only 100 feet up in the air. So you know the kite's not directly overhead because that's impossible. 200 feet of string, but it's only 100 feet up in the air. It has to be at a slant. It doesn't necessarily have to be in this direction. The slant could be that way, but this is certainly possible. So the kite is 100 feet up in the air. And now what you're told in the problem, it says that the kite is going to move horizontally at a rate of 8 feet per second. So we know anytime it says horizontally, you're supposed to assume that, okay, then the vertical is never going to change. Please notice I did not put a variable for the height of this function. I said the height was 100 and then this is changing. So the horizontal is changing, which means not the y, only the x component is changing. So I did label the horizontal down here x. And I can say, well, then this rate that the kite is moving horizontally at 8 feet per second, That's going to be my dx dt in this problem. So now I came up here and I said, well, let's go ahead and solve for what x is. We know that at the point of interest, 200 feet of string had been let out, and that the height was 100. So the x component here is just going to be the square root of 200 squared minus 100 squared. 200 squared is 40,000. 100 squared is 10,000. So we get the square root of 30,000 there for a horizontal component. Now, I needed to find out how fast this angle is changing. Now, make sure you can think of in your mind, if this kite continues in a horizontal fashion, please notice that angle is going to get smaller and smaller and smaller in order to get to that position. So I can say, I know this angle theta is decreasing with respect to time in this problem, but the way that I find it, I'm going to say the tangent of theta. And please notice the cosine and the sine would fail miserably. And you think, why would they fail miserably? Both of them depend upon the hypotenuse, and I don't have a clue what the rate of change of the string being let out is. So it's not always 200 feet, but I don't know how fast the string is changing, so I can't use anything in terms of the hypotenuse. However, if I let the tangent of theta equal opposite over adjacent, we know the opposite side, it's not changing, it's a constant. And the adjacent side, we know exactly how fast it's changing. It's changing at a rate of 8 feet per second. So the tangent function works beautifully here. I go ahead and I say the tangent of theta is equal to 100 over x, which, to make the derivative easier, to avoid the quotient rule, I called 100x to the negative 1. Now, derivative of tangent is secant squared of that angle times the derivative of the angle. That's where the d theta dt comes into play. On the other side, negative 1 comes down in front to give me negative 100 x to the negative 2 times the derivative of the variable dx dt. I plug in what I know. Now, a lot of students would really struggle from here to here plugging it in. They'd be like, where did you get that from? You don't even know what theta is. No, you don't. But you do know what the secant of theta is. So remember, guys, your right trig triangle, SOHCAHTOA, you know that the cosine is the ratio of the adjacent to the hypotenuse. Well, secant's the reciprocal of the cosine, so the secant has to be the ratio of hypotenuse over adjacent. That's where this comes from. The secant of theta is going to be hypotenuse over adjacent, and it's secant squared, so I just square that quotient. d theta dt is what I'm solving for. On the right-hand side, I have negative 100 over x squared. Well, that's going to be over the square root of 30,000 squared, times dx dt, which is a positive 8. So now, d theta dt is going to equal your, I went ahead and said that's going to be negative 800 over 30,000. And then you need to multiply by the reciprocal of this quotient right here. So I know I'm going to have a 30,000 in the numerator. The denominator would be 200 quantity squared, which is where the 40,000 came from here. Then the 30,000s cancel. You'd have negative 800 divided by 40,000. That reduced to negative 1 over 50. Negative 1 over 50, same thing as negative 0.02. Now, some people mistakenly want to think that this answer is in terms of degrees. It is not. This answer, and the answer you always get from any of these, is always automatically in terms of radians. So I didn't specify in my problem what I wanted your angle in, but let's say, for example, I said I wanted it to be in degrees per second. So this would be the radians per second answer. If I absolutely wanted degrees per second, it's no big deal. You'd just go in here and say, well, I need to get rid of my radians, so I divide by pi radians. I multiply by the equivalency to that, 180 degrees. And when I did that on the calculator, of course, the downside of this is you're getting a decimal approximation anytime you have to divide by the pi. But when I did that, and this answer is a little bit more meaningful, you can see that the kite would be decreasing by 1.146 degrees per second at that instant in time. So when 200 feet of string have been let out and your kite is 100 feet up in the air and going 8 feet per second to the right, that angle of elevation from the ground is going to be decreasing at a rate of 1.146 degrees every second at that instant in time. Moving on. You're like, well, that trig question was pretty cool. I bet these will be too. The nice thing about these is that they both require the wonderful law of cosines from your from your pre-calculus class. Number 2, you're told that two sides of a triangle are 12 meters and 15 meters in length. The angle between them is increasing at a rate of 2 degrees per minute. How fast is the length of the third side increasing when the angle between the sides of fixed length is 60 degrees? Please notice in this problem, this does not in any way tell you it's a right triangle. You cannot make that assumption. So I'll say, okay, for number 9, what can I assume? Well, exactly what the problem said. You have two sides of a triangle that are at an angle of 60 degrees between them. You have a 12-meter side and a 15-meter side, and the angle between them 60 degrees. Now, since these sides are changing in length, well, actually, are the sides changing in length? No, they're not. They're a fixed length, and what's changing is the angle between them. So actually, I did not need to label this side X and this side Y because they are not varying in the problem, so I really don't need the variables. I could have just called this side 15 and that side 12, and then I don't know this side, and it is changing, so I have to call that a variable. The goal of the problem is to find out how fast that third side is changing, so you'll see I called it dz dt. Now what we're given is that the angle between the two given sides is increasing by 2 degrees per minute, and we're supposed to find the accompanying change of the third side of the triangle. Now that 2 degrees per minute, I went ahead and converted that to radians because you can never multiply by degrees within any equation. It's just invalid. You have to have the radian measure. So I went ahead and converted 2 degrees to radians. I divided by 180 degrees, multiplied by pi radians, and said, well, that would just be 2 pi over 180, which reduces down to pi over 90 in radians per minute. Now, the law of cosines just says that any side squared of a triangle is equal to the sum of the other two sides squared minus twice the product of the other two sides times the cosine of the angle opposite the side you're looking for. So now in this problem, in order to solve for z, you can say z squared is equal to 15 squared plus 12 squared minus 2 times x is 15, y is 12. The cosine of 60 degrees, that's 1/2. Now that 1/2 and that 2 we have to cancel, and you just have 15 squared plus 12 squared, that'd be 225 plus 144, and then you'd be subtracting from that 15 times 12, which is going to be 180, and when I did that, I had z squared is equal to 189, which means z is just the square root of 189. Now, in order to find something out about dz dt, so I had to plug things in to find out the length of z. Now, in this problem, anything that varies must have a variable before I can take the derivative. So notice here when I'm trying to set up my derivative equation, z is varying, so it must have a variable. What I called x and y, they're not varying, so I don't call them x and y in this formula. I just said 15 squared plus 12 squared minus 2 times 15 times 12, and then the angle is varying, so I had to put the cosine of theta, not the cosine of 60 degrees. So that's a differentiable function that has to have the derivative taken on it. So then what I went ahead and done is I took the derivative. I said, well, derivative of z squared is going to be 2z dz dt. On the right-hand side, I just looked at this real quickly and I said, well, this is going to be negative 360 cosine theta. I know derivative of these constants, 0. Derivative of negative 360 cosine theta, well, derivative of cosine is negative sine, which changed the sign on this 360 to a positive 360 sine of theta, times the derivative of the angle, d theta dt. So now my goal is to solve for dz dt. dz dt is going to equal my 360 sine theta d theta dt. You'll notice I said 360. Once I've taken the derivative, I can plug things in. The angle of interest is 60 degrees. D theta dt, you cannot put times 2 degrees there. It'll give you the wrong answer. So I had to put the accompanying term in radians and say, well, that's pi over 90 for d theta dt. Again, not the 2 degrees. In your denominator, I'm dividing by the 2z, well, 2 on the square root of 189. This problem simplifies gorgeously here. Notice that the sine of 60 degrees is the square root of 3 over 2. That's really the only thing I've changed in that step. But then I said, well, I have 360 divided by 2 divided by 90 divided by 2. Well, 2 times 90 is 360. You have 360 divided by 360. All of those cancel. So then I have the square root of 3 times pi over the square root of 189. 3 will go into 189 63 times. So this simplifies to be pi over the root of 63. That would be an excellent exact answer. If you wanted a decimal approximation, you could go to your calculator. You could say, so this third side of the triangle is increasing at a rate of 0.396 meters per minute at the instant when that angle between these other two sides is 60 degrees and is increasing by 2 degrees per minute. So as that angle increases from 60 to 62 degrees, the length of that third side is going to increase by 0.396 meters per minute. Gorgeous problem there. Last one in the section. And again, this is going to be a law of cosines problem. I'm trying to make sure I cover all the different types of problems. In number 9, you had a law of cosines problems with fixed length of sides, and the angle between those sides of fixed length was changing. Now in this problem, I'm going to have the angle between the two sides is fixed, but the length of the sides is changing. Notice I say two people start from the same point. One walks east at 3 miles per hour. The other walks northeast at 2 miles per hour. How fast is the distance between the people changing after 15 minutes? Okay, so my solution to that, I drew out my little diagram, and it's not a very fancy diagram this time. Two people leave from the same point. One person is walking east at 3 miles per hour. The other person walks northeast at a rate of 2 miles per hour. Now you're supposed to remember, northeast, that's exactly in the midpoint between east and north. So it's 45 degrees angle between the two. So I can say, oh, okay, northeast is 45 degree angle from the person walking east. The person walking east is walking at a rate of 3 miles per hour. I labeled the distance that was walked east by x. So I can say that distance is going to be 3 times they walked for 15 minutes, which is 1/4 of a mile. Sorry, 1/4 of an hour. 3 times 1/4 gives you that person traveled 3/4 of a mile, or 3/4 of a mile. The person walking in the northeastern direction is only walking at a rate of 2 miles per hour. So I take distance equals rate times time, rate of 2 miles per hour times a time of 15 over 60, or 1/4 of an hour, and you can see that they have walked a distance of 1/2 of a mile. Now this is not a right triangle again. I need to find the distance of z. So I say, well, z squared is just the sum of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the angle opposite the side I'm looking for, which is the cosine of 45 here. I plugged this expression into the calculator, and I got the 0.282169941 for z squared. We need the square root of that. I have an ugly approximately equal to sign there. My ink kind of blobbed. And I got 0.5311966,812 for my value of z. Now, that's how far apart they are at the point of interest. But that's not my goal of the problem. My goal of the problem is to find out how fast that distance is changing. Is it increasing? Is it decreasing? And we know it's increasing because the two are walking away from one another. So how fast is that distance increasing? I know dz dt is going to be positive. Well, let's find it. I use the exact same equation. Now I need to remember, unlike what I did up here where I just plugged everything in, now anything that varies must stay a variable. So you say, well, the distance z is varying. The distance x and y, they are varying, so they have to stay a variable. But the angle between them, that's not changing, so I can go ahead and plug in the cosine of 45. And rather than getting a decimal there, I would prefer you just keep in mind the cosine of 45 degrees, that's just our square root of 2 over 2. So I plug the square root of 2 over 2 in for that in this next step. That 2 and this 2 canceled, and I just had minus the root of 2 xy for that third term on the right-hand side. Now at that point, I just took the derivative. So you see 2z dz dt equals 2x dx dt plus 2y dy dt, and then be careful here. This I had to use the product rule on. You have the differentiable function x times the differentiable function y, and the entire product is being subtracted. So you'll say minus the root of 2 times the derivative of x, which is your dx dt. So this derivative of the first times the second, and then minus the first, the root of 2x, times the derivative of the second, which is where your dy dt comes in. So now, once you've taken the derivative, you just plug in what you know. So, and we know everything now. Our 2 and our z, I plugged in the z along with the 2, dz dt is what I'm looking for, equals on the right hand side. I had 2x. Well, I know that x was 3/4 of a mile, so I said, well, 2 times that is just going to be 3 over 2 times dx dt. Dx dt was how fast x was changing. That was my 3 miles per hour. Is going to equal 2y. Y was my 1/2, so I said 2y is 1. dy dt, and in this case, that was our the dy dt from the problem was the rate at which you were traveling northeast. That was the 2 miles per hour, so I put that in. Minus the root of 2, and then I can say that the root of 2 in this problem is going to be multiplying the dx dt, which is how fast you're traveling east, the 3 miles per hour, times y in this case are 1/2, and then minus the root of 2 times x. We know x was 3/4, and we know our dy dt was the rate at which you were traveling northeast, 2. So now I can say dz dt, and it looks like I forgot to correct. I'd made a mistake in that numerator, so I'd whited it out. Whited it? It's not even a word. I'd cleared it out. Let me do that numerator here for you. That's just what I had on the right-hand side. So I would say 3 over 2 times 3. We know that that's just going to be 9 over 2. And then I'll have plus 2. And then my last two terms, I'll have minus 3 on the root of 2 over 2. This is going to be minus 3 on the root of 2 also over 2. So in order to get those last two terms, I might as well just say minus 3 on the root of 2. I'd be subtracting it twice over 2, same thing as that. So my numerator here is the 2.25735. And it's not writing too well over that whiteout. 9313. And then you can see when you divide that by your denominator, you get to the answer I had there. So my denominator was just my other side there. I would be dividing by the group 2 times 0.5311966,812. And this, ooh, what did I do there? So let me fix that error. Sorry guys. 2.257359313. We're dividing that by the group 2 times 0.5311966,812. When I do that, I get to my final answer. Yes, and I had it rounded to 3 decimal places. So whenever the instance of this problem happens, the one person is walking 3 miles per hour east, the other person is walking 2 miles per hour northeast, then at the instant 15 minutes after they started walking, they're moving away from each other at a rate of 2.125 miles per hour. Now that is only the rate of change at the instant of 15 minutes. What if I want to know 16 minutes, 17 minutes, 18 minutes? You'd have to go back into your problem all over again and change all of your variables, because that's going to change the distance of x and y however many minutes that have elapsed, and it will change the overall problem. But we can say at the instant of 15 minutes at least, we know that this rate is 2.125 miles per hour. All right, guys, hopefully this helps you with related rates. It's a concept a lot of students really struggle with. Please let me know if you have any questions.